option to record here. Cool, I think I'm recording.
Hey.
Yep. Quick time. And I can also see you here in my lower screen, which is great. The sum of both diagonals. Any questions on the premise of the problem? Cool. So we should get 30, right? For this matrix, because it's 15 one diagonal, 15 the other one. So let's have a function here. Actually, I'm gonna remove this stuff. Or not remove, I'm gonna leave it here at the top. I also can share this with you. I'm not sure, invite. Oh, here, I'm gonna copy this, send it in here in this chat so that you can have it also open. Where is the chat option here? Here, boom. Cool, so you can also have access to the code directly. This is cool. Okay, so let's do const sum diagonals sum. Let's call it. This takes in a matrix. And we have to sum the diagonal. So how could we break this problem down into smaller pieces? How could we?
Will our input always be 3 by 3, or do we need to account for possibly larger or smaller matrices?
A good question. Let's start with a perfect square matrix, and then from there we can think about how to have one that is not 10 by 10. Give me 1 second. That's coming. Technical difficulties. Vesa was left out of the room. I'll be back in 1 sec.
And so like $1,200 for
cool.
individual people, and families get more per child. And that should be next 3 weeks. Yeah.
I did hear as well that possibly if you are not set up in their their direct payment, like direct deposit ecosystem, it might take longer for a check to be rolled out to you. But outside of that, yeah, no, this is good news.
It is.
Oh yeah, my ex is gonna get it for sure.
Well, so will you, right?
I'm not in the system because we filed together. I don't know how that works.
Oh, so then if you file jointly, then you get as a couple $2,400.
Woohoo! And kids?
Kids get $500 each.
So 2,900? Nah.
Depending on how big your family is, yeah, you get $500 per child.
Oh, I should have filled the emergency pursuit thing then. If I'm getting 2,900, whoa.
Well, I don't know. I didn't exactly read the bill. I'm just going by what CNN is telling me. So who knows?
Cool.
I've been obsessed with.
That's a lot of money, 29.
It was. Put that in a matrix.
That ain't nothing.
No, and if it's for just a couple of weeks, it's good. But if it's supposed to last us for months of being, jobless or whatever situation some people are in, it will really go fast.
Cool.
I would try to invest it and make more out of it.
Okay.
What would you invested in? The markets are down. Like there's no money to be made right now.
Bye.
Guys, we're about to start back with the lesson.
Okay.
Sorry.
Can you guys hear me well?
Yeah.
Great. Okay, so we said let's focus on a 3x3 grid. Let's do, then how do we do the first diagonal? We want to sum all the numbers that are on the first diagonal. How can we do that?
You have to create a variable first.
Actually, yeah. Actually, before we do that, something that helps is like describing what is the first diagonal and trying to see if we find a pattern. So let's describe the first diagonal here. So what is the location of the first element in the first diagonal?
0, 0.
0, 0. What is the second element in the first diagonal?
1, 1.
1, 1.
1, 1. The third one?
2, 2.
2, 2. Cool. So here we found a pattern. What's the pattern?
Both X and Y increase by 1 at each step.
Correct. Both are increasing by 1 at each step. Okay, so we know that wherever we're going to add the sum, we need to visit 0, 0 first, 1, 1 after, and 2, 2 after. We could talk here about like coordinates, X and Y, index I and J, whatever we want to call it. So let's do that one first. Let's try to do like, let's console log the numbers that are on that first diagonal. So how could we start doing that?
With a for loop.
Okay, well, guide me here more. What do I type in its for loop?
If I is less than matrix.length, I++.
I++, okay. Then what? So we have I starting at 0. So what happens if we do this? Console.log matrix at 0 or sub 0 sub I. What are we going to get if we do this?
Error.
Nope, we're not going to get an error. Or
That's a lot.
If we're looping, oh no, I think
Thank
I
you.
got, yeah. We would get 1, 2, 3.
we'll get 1, 2, 3. Let's see that. 1, 2, and 3. Douglas, do you want to explain why we got 1, 2, 3?
Sure. Because we're hard coded into the first. It's only ever going to look at the very first matrix or the first array in the matrix, which contains 1, 2, and 3. And it's going to start off, technically I is 0 to start off with. So it'll print off 1 to start, and then it's going to loop again, and then print off 2, and then again, and print off 3. And then since there's no other numbers, it'll just stop.
Correct. So here we sort of latched onto the first array, the first subarray, right? And we're increasing I, which means then we move from 0 to 1 to 1 array 0, number 1 array index 1, number 2, index 2, number 3, and so on, and that's what we get here. So we're moving like horizontally. We're not moving diagonally. Let's hear actually another question here. What if I try to do this? I here and 0 here. Savita, what do you think we're gonna get?
You would get wait, 0 and I.
So when we have 0 here and I here, we got the first row. Basically, we got 1, 2, and 3, which is the first row, right? Now we're flipping this, and I'm putting I here and 0 here.
Oh, you would get 1, 4, and 7.
Correct. Right? Let's run that. 1, 4, and 7. Why 1, 4, and 7? Could you elaborate?
Because when you're looping, I is giving you 1, 2, 3, and 0 stays the same, the first position.
So we're saying the first position of every subarray, and we move on each subarray, right? But we want the first index, index 0 of each subarray. Then we sort of move in vertically, right? Now we broke the pattern here, so we know that if we go 0, 0 for the diagonal, both x and y, I and j, whatever you want to call it, is the same. So what we need to do then here, what happens if we do this? What are we going to get now?
Everything.
Everything? We wouldn't get everything. But let's think about it. Like we saw that we moved horizontally and vertically, depending on which one we put I.
Okay.
Start here.
You're gonna get the diagonal, right?
The diagonal, right? Because we get 0, 0 on the first iteration. Let's put here. There's actually also console log I here. I is going to go to 0, starts 0. So this is going to be 0, 0. Then it goes to 1, 1 and 1, 2, 2 and 2. Let's take a look at it. The second number is the actual number. The first one is the index. Questions up until this point? And we can do it with just one variable. We didn't need x and y, or we didn't need I and j. We could have those, but since here the pattern is both increase on the same, then we don't really need that second variable for the inner one. The pattern here was the number is the same, right? Okay. Any questions? Cool. So can we sum? Who can add here? How to collect that sum? Giselle, let's do. How could we collect? We're constantly logging the elements, but we actually want to collect the sum of the first diagonal. How could we do that?
You could first state a variable before the for loop and just have it accumulate inside the for loop. So you can have like a, what's it called? A plus equal. The matrix at I.
Okay.
So accumulator plus equals matrix at I. So through every iteration, it would just add that value. And then for the first diagonal, and then the second diagonal would just be the for loop but backwards, I think.
That's correct. So let's do this. Let's return the accumulator. And let me put a console log here.
Matrix spelled wrong.
Thank you. I don't know what my matrix spelling is not working today. So let's do that. Let's return this. Cool. We got our first result, 15. Great. Thank you, Winter. Okay. I actually want to give you some time to do the opposite one. I think Giselle already described it. You sort of do the opposite. So maybe in a separate repo that you have, try to do the opposite one. You can copy and paste this code if you need to. Let me give you 5 minutes for that. I'll be back in a sec.
Can someone explain what he means by opposite?
So you will be adding together 3, 5, and 7.
Okay, thank you.
No problem.
Give me a thumbs up once you're done. Okay, thank you. Thank you, Winter, for the timekeeping. Appreciate it very much. Can we have someone paste their code in my repo? But let's figure out who that's going to be. Raise your hand or your thumb if you are done. I think I saw Douglas and Giselle. Nobody else is done? The second part? Okay, let's take a look at Douglas's code.
I'm sorry. Actually, I did it on a whiteboard quick.
Oh, I see. I see. Got it. That's a little bit complicated. Sure. You want to do it? No? Okay.
I could talk my way through it real quick.
Sure. Yeah, let's do that.
just so we're not holding things up. I don't quite know if this fully works because again, I wasn't working in a coder. I was trying to be quick about it. But we've got a loop that's doing all the hard work for us. So I figured I would just simply make like another accumulator of the sort. Right below ACC, I did REV plus equals matrix at matrix.length minus I in both of the two subs. So that way that would, like, the I would increase, it would minus by 1 for each one, but technically it would start at the length of the matrix and then subtract by 1 until there was no more.
I like that. Did you do it only with one loop?
Exactly, yeah. So it was, since the one loop was doing all the work for us, just below ACC plus equals matrix at I, or sub I did REV plus equals matrix sub matrix dot length minus I sub matrix dot length minus I.
So let's do it first with a second loop, and then we can see how that works.
Okay.
So some of you have my code selected. Could you please deselect it? So as Giselle mentioned earlier, we just need to do the opposite. So let's think about what is the opposite. Similar to what we did here, this was like the pattern for the first diagonal. I'm gonna write here the pattern for the second diagonal. So it's this one. So the pattern for that will be 0 and 2, right? Because that is on the first array, the second element. Oh, thank you. Yeah, you're typing. You can go ahead. Mm-hmm. 1, 1, okay. And the other one, the last one. Right, so this is the pattern for the second diagonal. 0 and 2, 1 and 1. 2 and 0. So what do we have here? Let's see. Let's start on like this side. We see 0, 1, and 2, and on this one 0, 1, and 2 in the opposite direction. Wait, can we do this with 2 loops? Because maybe what I was thinking is not accurate, actually. 2, oh, I guess it is, it will just be starting here. Oh no, it's the same thing. This is what I was thinking about. Let's take it a look. For let's say J equal to matrix dot length minus 1. So we start at the end. Then we do J minus minus. Well, as long as J is greater than 0, greater or equal to 0. So we start at the end, and then let's try to do this. Basically, same thing that we had here. Thank you for that correction. Let's take a look at this. Instead of I, let's do that with J. Let's not do the accumulator just yet. Let's try to do this. Just take a look. So we get 9, 5, and 1, which is the same as the first diagonal, but in the reverse order, right? We get 9 first because that is at J2, 2. We get 5 next because that one is at 1, 1. and we get 1 because that one is at J00. Okay, so that's, I was thinking that in this way, we could do the other diagonal, but this pattern here is not the same as our initial pattern, the one we're drawing here. Our initial pattern is like they all increase exactly the same. Now for the second one, we see that one has to increase and the other one has to decrease. That's then the pattern. I has to increase, J has to decrease. So let's do it here as a separate one, and we can see how we can do it with one. So what if we do this? Let's do, I'm gonna have another I here. Actually, do you know that you could do this? You could say, let J start at the matrix length and I start at 0. So you can have your initialization. You can initialize more than one variable there. And same thing here. We can do more than one of these. So we said J has to decrease with, let's say this is J and this is I, and I has to increase. So we're increasing that. Let me do it here first, and then we can format it. So here we initialize J and I. Then we say, because J and I are the same, we can just say, as long as J is greater or equal to 0, let's decrease J, let's increase I. And then let's try to do matrix at index I, J. And let's also do, let's do this here. Let's do I. Actually, let's start I first. Like this. Let's give it a run. Cool. Let's take a look at what we're getting at. We're getting 3, 5, and 7. That's 3, 5, and 7. Right? That's the diagonal that we were looking at. Now let me format this a little bit. The way that I will format this is something like this, but it's weird. It's weird to have this kind of, it's a little bit weird to have this kind of loop where you have more than one initialization. So this is what we initialize first. Actually, let's do this. Initialize 2 variables. And then for each iteration, we are decreasing J and increasing I. Cool. We could have also done the same thing here at the top for the first diagonal, but as we realized that here the pattern was easier, just increasing at the same, both going up at the same rate, but here is one is going up, the other one is coming down. Then we require this other variable I. And then here we can just do accumulator plus the matrix sub I sub J, and we should end up with 30 as our result. Plus equal. And we should end up with 30 as our result. Any questions on this part?
Me.
Yes, sorry.
It says that J should be greater or equal to 0.
Yeah.
But what about I?
That's a good question. What about I? So we don't have to care about I in that sense because I and J are the same length, right? We have a perfect square matrix. So we know that J already covers for I as well.
When that condition is met, it's good for both. Okay.
Correct.
So
Correct.
Also another question, like I was trying to do it a different way, like I couldn't finish because I couldn't kind of visualize it, but instead of having 2 variables, have one.
Yep.
And define the other by the difference between the the matrix length and that.
I think, yes, that's correct. That's the approach that Douglas was mentioning, and that's what we're going to see next.
Okay.
Yep. Other questions? Joanne or Savita?
Yeah, when I was doing it, I guess because I didn't do it this way. I kept getting well, I got 44 as the result, which is completely wrong because I kept getting like the backwards of the first diagonal.
That was my first thought as well, and I was wrong. On that, you know, I would just get the first diagonal in the reverse order.
Yeah.
Cool. So here is
super quick question. I'm sorry to interrupt. Is this a nested loop, or is this all one loop?
This is so what we have right now is two loops.
Oh yeah. Oh yeah. I
loop.
forgot that first one there.
Yep.
Sorry about that. Okay.
That's okay. Sometimes you might also see this. I think I prefer for loops just to have like one condition, one initialization, and one increase. Sometimes you might see this written in the following way. Like if we write this as a while loop, it will be let I 0. Let's see if I can type. Does j equal to matrix dot length -1, while j is greater or equal to 0. ACC plus equal matrix I sub j, and here I plus plus, sorry, yeah, I plus plus j minus minus. I find that sometimes while loops are better organized, easier to read. Let's just verify that we get the same result. We get 30, where we have I starting at 0. And then here, basically, we are, and this is what we do in programming. We describe patterns in programming. Here, we're describing this pattern. I going up and j going down. Cool. Any questions about this other with a while loop? Okay. Let me add a comment here. Below. Cool. So then we have something that is able to do the sum of both diagonals. We have two separate loops. The time complexity of these will be, what do you think? What is the time complexity of this algorithm?
The first and the second one.
The diagonal sum as a whole function, what is the time complexity of it?
Is it O of n?
Correct. Why?
Because it's dependent on how large it's. I've already forgotten the name of the word. It's not linear. Where it's it's dependent. It has to go through each loop. But even though it's doing two loops, it's not like a nested loop, so it's not squared.
That's correct. And also, even though we have nested arrays, you could say, oh, we have nested arrays, it'll be O of n squared. But it's not, because we're not visiting every single element in the matrix. To visit every single element, we will need an O of n squared algorithm. Because for each subarray, we need to visit each element. And that will make it O of n squared. This is O of n, and something that can be a guiding question is how many operations are we executing per, or how many operations does this algorithm need to execute to finish? And we saw that it was, well, in the operations, I mean, how many times do we add up to accumulator? We got 1, 2, 3, and then 1, 2, 3, or 1, 2, 3. not 6, 4, 5, 6. So 5 operations, six operations in total that are being made in 2 separate loops, where each loop is where the number of operations is basically the length of the matrix, or the length of any of the inner arrays. Because here again we have a perfect square, and we just traverse the matrix. We need like 3 operations on one side, 3 on the other one. Linear, like it will be linear time of n, where n is the length of the matrix. Cool. Now let's take a look at how to do this, as Douglas and Sergey were suggesting, with just one loop. So maybe let's do it here. Const diagonal sum 2 matrix. We're going to need the basic first loop, let I equal 0, I is less than the matrix length, I plus plus. So we know that this that accumulator is starting to 0, and we do accumulator plus equal matrix sub I, we know that this sums the first diagonal, right? Now we could take the advantage of analyzing the pattern again to actually do it in one. Let me take this back. So we got this side cover increasing, but could we cover this other side as well? Could we cover the other side as well? So we know that, like, if we think about like this being I and this being J, and this being I and this being J, we know that I is increasing on both sides, right? For both kind of operations. Now J here is going up, so maybe here then we don't use. Here, this could just be I, right? That's what we did on the first one. It's just increasing. But then here, how could we describe this one? If we could only describe the J in terms of I's, basically. That's what we're trying to do. Describe this J pattern in terms of like what I is doing. And it turns out that then this 2 is just basically, this 2 is the result of having matrix that length minus I, right? If we think about on the first iteration, I is 0, the matrix length is, the matrix length is actually 3. So we're gonna catch an error here. The matrix length is 3, right? Now I is 0, so 3 minus 0, that gives us 3, which will be an out of bounds, and we need these 2. What that means is that we need to subtract 1 here, right? Let's subtract 1, so then matrix that length minus 1, that's 2, right? Then that gives us this 2, right? And then let's subtract I from that. So 2 minus 0, that's 2. Let's see how that holds in here. Now we have I being 1, and then let's have sort of our J be matrix dot length, which in this matrix dot length is a constant, it doesn't change, is 3, minus 1, 2, minus I, where I is 1, that will give us 1. So we got, the matrix length, we know is a constant, 3 minus 2 minus 1, minus 1 minus I, right? This will give us 3 minus 1, 2, 2 minus 1, 1. And it will be the same here. This is content, minus 1, minus 2. Questions regarding this, what we're describing here?
Would it be better form to put a to park that matrix.length -1 in a variable, so that way it would be simply when it comes down to using it. I'm maybe getting a step ahead. So it's not matrix.length -1 minus I. It would be like reverse matrix minus I, if that makes sense.
Wait, I don't think I understand what reverse matrix is.
No, just making up a variable name and parking matrix.length -1 as the value of that variable, and then assigning that to in the
Yeah, we can definitely do that. But I wanted to make sure that everyone sort of got the pattern of how we got a J with respect to I. How we're using I sort of to derive our J, by identifying that we could just use the matrix length -1 minus our actual I at that point to get the J that we're getting, that we want. Does that make sense?
Yeah, that's what I was trying to do.
So in that case, then we have everything sort of based to I, which then tells us, oh, we can do it in one loop. So what that will look like is we have our I ready to go. Let's have our J. Let's do it after this. So let J is going to be equal to, we could have the matrix length in a variable. I don't think it's actually going to be necessary. We could do this matrix length -1, literally what we did before, minus I. And then here we just add to the accumulator with the plus equal matrix sub I. No, is it sub I? Yes, sub I sub J. And the return here, the accumulator. Right. Now let me have this, I'm gonna comment this one out. This, put the 2 here. So we actually use this diagonal sum 2. Also, I want to console log here. The console log here. So let's see if this works first. Run it. But we got the same result of 30. So note that this part takes care of the first diagonal. Then we calculate the second one. Let's console log here, I and J. And if we look at here, what we had written here is literally that. That's our pattern, 0, 2, 1, 1, 2, 0. And it's just that here, this is just I, so we just take advantage of that one. That's always increasing. And we can use the same variable to keep that going for the accumulator. Questions, thoughts? Oops.
If somebody fell out of the group, how do you get them back in?
Oh, I think I'll have to go. I'll have to go. The Zoom is incredible technology. They definitely need some work. You guys should be looking at Zoom to see if they have openings. I'll be back in a second. If you have any questions, leave them in discuss with Winter. I'll be back in 1 sec.
Never heard of it.
Oh, this is interesting.
This is helping out a lot.
Wait till
like-
Alejo come back. Oh, he's back. Oh,
I was thinking that yeah, Zoom is so many windows open and like they're all small and like they got lost. They should have like a way to centralize everything.
The
Master
post
control.
attendee tabs the infinite amount of post attendee. You see that?
Wait, what?
Whenever you open a Zoom, there's like a tab in your browser that says post attendee or something like that.
Oh yeah.
I hate that.
Anyone? Somebody had a question?
I had just said I was thanking everybody for walking us through this. I appreciate it a lot.
Sure. Cool. So this makes sense how we're taking advantage of I to calculate our J. Great. Going back to the initial question about, like, I think Douglas, you mentioned, what if it's not a perfect square? What if it's something like this? 10, 11, 12. What would we do in that case? That will depend on like what you're trying to do or the interview. If you know if you ever get to see this in an interview question, because like here there is no, you could do this diagonal. What is the second diagonal? Like the second diagonal will still be what you have here, and this will be left out. So for some, stuff like that will be dependent on what you're doing, what the context of the question is. For this case, like we can't really do that, or maybe in this case will be like, well, sum all the diagonals. Let's say sum all possible diagonals. Here will be this diagonal, then this other diagonal, then this diagonal, and this other diagonal. I guess that could be the next question. There. Okay, cool. Any final questions before we move from this one? I just want to do a pulse check with Savita. Savita, are you with us? Hello, Savita. Maybe she's not with us, which is really sad.
She said she is. She's in the chat.
She can't turn on her mic.
Oh, got it. Cool. Thank you for that. Okay, so let me save this.
Sorry, it was on another screen and I couldn't get to the screen for the mic.
Okay. Yeah. Any questions on this?
I'm gonna have to go over this on my own.
Okay.
It's not. I don't really get it.
It's like the trick here is identifying the patterns, how they were both increasing for the first diagonal. So we could just use I for both because I increases from 0 to 1 to 2. And then for the second diagonal, we describe that this is the pattern. We start 0, 2 on the first element, then 1 and 1, these two are actually the same, and then 2 and 0 for the last element on the second diagonal, the diagonal that goes right to left. And then we talked about, okay, we got I is given to us, we have I increasing already. Can we calculate a J based on I? And we said, yes, we can calculate a J based on I because we realized that we could use the matrix length minus 1. So in this case, the matrix length is 3 minus 1, and we can just subtract I and we get 2. Matrix length 3 minus 1, 2, 2 minus 0, where I is 0 on the first iteration, we get that 2. And then that pattern just repeats for the other one. We have the matrix length 3, minus 1, 2, minus 1, 1 at the end, and we get our new result. Let me put this here. 2, 0. Oh, let's do this. So that is actually 3 minus 2. Is 0. And the pattern is basically this one, minus I. And based on the value of I and the matrix length, we are able to derive our second value to be able to get that second diagonal into one loop. So yeah, if you feel like you need to review it, make sure to spend some time after taking a look at it. Okay, let me take a look at what we had here. So that maybe instead of going, let me close this, close this, close this. It's cool. We did tic-tac-toe with some of diagonals. Cool. So should we do this one? The two-plex matrix. Did anyone did this one? So a two-plex, I don't know if I'm pronounced that correctly. Two-plex matrix is a matrix where every left or right descending diagonal has the same element. Given an empty array, write a function that returns true if and only if the two-plex matrix, if it's a two-plex matrix, basically. The matrix can be any dimension, not necessarily a square. Let's try this one. I think I've never really solved this one myself, but since we have in the context of diagonals, I think we can move on to that one. Let me go back to here. I'm actually going to change the name of this to be some diagonals, some. And just, save. I don't know if the people that were there get kicked out. I'm going to share these in just online resources right now. Oops. So that we have it. I'm going to create a new REPL. Let's call this one two-plex. Invite you all here. So you can join me there. Let's then try this thing. Let me close VS Code and I'm not using it. Copy this here. And comment all this stuff. Okay. Okay. Actually, I'm going to give you 10 minutes to start an approach on this one yourselves. I'm going to, yeah, let's stop sharing my screen. Can everyone join? Maybe make a copy, select all the text and copy in your own REPL. And I want to give all of you, let's do 15 minutes. And let's reconvene here. So let's make sure to ask any questions. Thank you, Winter. How did it go?
I've come close, but I can't trigger a true. It keeps throwing an error that I can't parse.
Okay. Anybody else? No success. Let's see if we can get this in 15 minutes. Let me share my screen here. So just like we did in the other one, let's describe the patterns first. So we know that the first diagonal is 0, 0. So let me 1, 1. If the people that have selected stuff could move around so that it doesn't appear, it doesn't block us. And the second one is 2, 2, right? We said that this describes the first diagonal, right? Now let's describe the second diagonal, which is, this is the diagonal of ones, the diagonal of twos. Diagonal of 2 will be 0, 1, right? 1, 1. No, 1, 1, 1, 2. The next diagonal will be 2, right? So we get, this is the first, this is the second diagonal of the twos. This is at 0, 1. This is at 1, 2. This is at 2, 2, right? If we put the indices back here at the top, as we did in the before, we will have 0, 1, 2, 3. You have 1, oops, 0, 1, 2. Cool, everyone with me here? Okay, so we said the first diagonal is of the ones. That is the first number 0, 0. Second number 0, 1. 1, 1, sorry. This one, this one, this one. Second one, 2, 2, 2. And now let's think about the second diagonal, the diagonal of 2. So that one is 1, or 0, 1. We're describing this one first. 0, 1. Then 1, 1, 1. Wait, 1, 1? So 1, 2, right? This 2 is in row 1, column 2. So it's 1, 2. That's what we have here, the second one. The third 2 is in 2, 3. So then that's the third one here, 2, 3. Now let's do the third one. The third one will be this 3 and that 3. So who can do that one for me? The diagonal of 3s. We only have 2 numbers. What's their location?
0, 2, and 1, 3.
0, 2, 1, 3. Correct. Okay, do we see any pattern forming?
Yes.
What is the pattern, Joanne? Or maybe you could start describing it.
The index is increasing by 1 as you're going down, and It's also like even numbers. So when it's 0, it's 2, and then when it's 1, it's 3. So there's a difference of like 2.
Wait, could you say that again?
No, I'm saying there's a difference of 2 between I or J, I and J. Sorry.
So let's say we have this is I and this is J. And there is a difference of 2.
With the last one, but then
Oh, you mean here? There's a difference of 1 here.
Yeah.
And there's a difference of 2 here.
Mhm.
Oh, that's interesting. I hadn't noticed that. That might actually be of important detail. Let's do I, J differ, increasing by 1, 2. Maybe we can take advantage of that. What else? So we know how to do this one. We already did that one. We have to think about how to do these other two. Like here is, well, we see this is another interesting thing. Like I always gets back to 0 and goes 0 to 1, 2. It goes, goes back to 0 here, then 0 here, and it goes back. It goes up to 2 in both. And this one, I think this is what you were describing, Joanne. That J is like starts with I, but then on the next iteration, J starts at 1 instead of starting at 0. On the next one, J starts at 2 instead of starting at 0 again. Maybe that's something we can take advantage of. Excuse me. How could we then do this? So it seems like here we're gonna need I and J for sure. Maybe I'm thinking that maybe there's a way to do it like with I only, but let's try actually I think it's better if we do it by, oh wait, what's this? Just actually having I and J. Anyone has any initial thoughts? Please, how do you spell this again? Please, TZ. I'm gonna call it just M for short, matrix. Let's start. Are we going to need 2 loops? What do you think? Should 1 loop be enough? Any speculations? 1 or 2 loops?
2.
I'm thinking just 1, but I'm confused as how to get the diagonal of 5s.
Say that again. Which diagonal?
The diagonal of 5s.
The diagonal of 5s.
Yeah, the 2, 0 and the 3, 1.
That's correct. Let's try to think. I've totally missed that one. That's a good point. I didn't think about that one. Let's see. Let me take a look here. So I think we're gonna need 2 loops as well. Let's see here. The diagonal of 5s that I completely miss is 0, 1. 0. Wait, sorry. We said which number are we describing first?
I think it's the other way around. It would be subarray 1, index 0, and then subarray 2, index 1.
Correct. So we did get this. That's a good point that I didn't think about. Huh. I was wondering if maybe with a sort of a mathy way to do it, to get to those, we could try to do, yep. Yeah. Because what is the, well, the possible, the smallest possible matrix will be like this. Now, this is the smallest possible matrix in which we know that there's only one diagonal. Let's see two diagonals. I guess this will be 0, 1, 2. Even, okay, so even this one has, with star minus 1, let's do 1, 0, 1. In this here, we already have actually 3 diagonals. We have the 1s, the 2s, and the 0s. We have 3 diagonals. So for a 2 by 2, 2 by 2, we get 1. 3 by 3, we get 3. No, sorry. Yeah, 3 diagonals. 4 by 4, which is not exactly what we have. We have a 4 by 3, 4 by 4. A 4 by 4, what would we have? In a 4 by 4, we have the ones that we already have here and 1 extra. So we have the 1s, the 2s, the 3s, and the 5s. So we get, if we had this as an extra here, let's say 0, 6, 5, 1, we get this other diagonal of 6. So we got 1, 2, 3, 4, 5 diagonals. I'm just trying to see if we will find sort of a relationship between the rows, to know how to go to know how to go to the next diagonal that we might be missing. So we're able to sort of scan horizontally, and we know that wouldn't miss horizontally. We sort of did that scan here, but we'll need a way to also do that vertically. I think we're running out of time. I'll keep working on this. I'll encourage you to keep also working on it, and then we can come back together at some later point and actually do sort of the full analysis of it. I think that will be it for today. Let's head back onto the main room for the send off, and that'll be it for today. Any final questions or thoughts? Okay, see you on the other side.
Oh wait, do I need to jump out of this one, or does it automatically push me to the?
You have to click on leave breakout room.
Oh, I see it. Thank you.
a new array to the board of the appropriate
Actually,
length.
I got a better idea. Why don't we just copy the board like this? So now you have the copy of it, right? So now we can just look at the copy, and the copy never changes.
You have to spread it.
Oh yeah, spread it.
Okay.
So now this is just a copy, and we check the copy every time, but we can keep this that board.
No, that won't work.
Oh.
That won't work because each element of the board, you're copying the board, which is an array of arrays, but each element of that board is an array, right? You're not copying those elements. Make a new board. Just make a new board. It's going to be easier. I mean, you can copy it, and I like the copy strategy, but this won't work. You need to copy every single row.
Oh, the spread is only like one level?
That would copy, like, wouldn't that just be like a huge waste of memory? Because you're copying the board each and every single time you're updating.
Yeah, but you're doing that anyway. With the new board, you're still making two boards every time.
All right.
I don't know if this is a shallow copy or a deep copy. So if it's a deep copy, it's fine, but if it's shallow, it would not work.
It's going to be shallow.
It's shallow? Oh.
Yeah, of course.
Guys, we need to start heading back to the main session. We'll see you all there.
Okay.